Year 13, Chapter 10, Integration, Lesson 2, Integration by Substitution. So we're going to start off by looking at an example of an integral, and I want you to think about why it would be really inefficient for us to try and integrate this using the techniques that we might have learnt in Year 1 integration. So if you worked it out, you would have to expand this using Pascal's triangle or a binomial expansion, and then integrate term by term, which is a lot of work for what looks like a very simple integral. And yes, there is a much simpler way in which we can do this. It's called integration by substitution. We're going to introduce it in this lesson. So the first thing that we need to do is identify the fact that this is a composite function that is being integrated. And you can see that because we have an inner function here, 3x minus 7, which is then being raised to the power of 4. There is your composite. So I'm going to identify u, which is equal to 3x minus 7. It doesn't have to be u, it could have been t or p or any other letter. I've just chosen to use u. U equals 3x minus 7. And then we're going to differentiate that. So du by dx is equal to 3, and we'll come back to this in just a minute. So, revisiting my integral here, instead of 3x minus 7 to the power of 4, I'm going to write u to the power of 4. Now, I can't integrate u with respect to x. They're two different variables. So I need to have, instead of dx, I need to have du. So this is where I revisit this derivative here. Du by dx is equal to 3. Now, the next line of maths that I'm going to write down is not a proper piece of maths because du by dx is a derivative. It is not a fraction. It is not a division calculation. But I'm going to pretend that it is because that is actually good enough for what we're trying to do. So even though it's not precise mathematics, it is a good enough substitution, it's a good enough workaround to get us where we need to get to for the purposes of A-level. So I'm going to imagine that du by dx can be separated, and in theory I could write du equals 3 dx. In reality, this is not a real piece of mathematics, so I'm going to put this in a pair of quotation marks just to indicate that. I'm then going to rearrange this so it tells me that dx is du over 3. Now again, that is not a real piece of mathematics, so I'm indicating that using the fact that I've got quotation marks in. But it does allow me very simply to replace dx with du by 3. So I have this. And I now have an integral that I can complete, which is in terms of u. I can pull the factor of 1/3 out of the front of the integral. I then have the integral of u to the power of 4 with respect to u. So we then get 1/3 u to the power of 5 over 5, and of course we need to make sure we include a plus c because this is an indefinite integral. This now needs a little bit of tidying, so we have 1/15, and then instead of u to the power of 5, I remember that u is of course the same as 3x minus 7, so I get 1/15 3x minus 7 to the power of 5 plus c. And that is the process of integration by substitution. Now have a look at the original integral and the answer. So we started with 3x minus 7 to the power of 4, and it's become 3x minus 7 to the power of 5. And we've ended up with 1/15 in the denominator. Now there is a link here. It's a little bit like the quick chain rule. Let's do a few more examples and then we will hopefully identify how we can actually sometimes get from the original integral to the answer in one quick step. So the next question, x plus 6 to the power of 7 is being integrated. Notice the inner function is x plus 6, so I will say that u equals x plus 6. Du by dx is then equal to 1. And knowing that I'm going to have to replace dx here, I'm then going to rearrange this, again remembering that this is not strictly speaking accurate mathematics, but it is a good enough workaround to get me dx is equal to du. This then gives me the integral of u to the power of 7, and in place of dx, I've got du. So, raise the power by 1, divide by the new power, add c. And then, of course, we need to replace u with what it should be in terms of x plus 6 to the power of 8, and then there is a factor of an eighth as well. So notice that we started with the integral of x plus 6 to the power of 7, and then we ended up with an answer of x plus 6 to the power of 8 all over 8. So we've raised the power and divided by the new power. But in the previous question, there was something else that went on as well. And that's because in this question, we've got a much simpler inner function than we did in the previous question. So the inner function plays a part as well. And we'll look at a few more examples, again, to keep illustrating this process. So next example, 5 minus 2x all squared, the integral of, what's our inner function? U is 5 minus 2x. Du by dx is equal to negative 2, and then rearrange this, or pretend we're rearranging this, so that's in the form dx. So this is really, if this were algebra, this would be really basic algebra, and you would get this, which again, putting in quotation marks, as we know we'll need it, but we know it's not real mathematics here. So this is equal to the integral of u squared, and then in place of dx, I'm going to put negative du over 2. I can then pull out the factor of negative a half, so I'm left with the integral of u squared du. It's always easier to pull out these factors in front of the integral and then incorporate them afterwards. So that's negative a half u cubed over 3 plus c, or negative 1/6 u cubed plus c, and then of course we need to replace u with what it is from over here, so that's negative 1/6 5 minus 2x all to the power of 3 plus c. And again, be thinking, how have we gone from here to here? Yes, the power has been raised by 1, and we did divide by the new power, but then there's also this factor of 2. Or negative 2 really. How does that link back to the original question? Be thinking about this as we do a few more examples. So the next example is written as the square root of 2x plus 1 being integrated. So of course we really want to express that as power half. Now what is my inner function? It's u, which equals 2x plus 1. And then du by dx is equal to 2, and then we do our sort of faux rearrangement as we've been using. Remember, it's just a simplification that allows us to answer these questions very efficiently. So this then becomes the integral of u to the power of a half and du over 2. So we've got a half, the integral of u to the half du, which is a half u to the 3 over 2 when we raise the power by 1. Now remember, we're dividing by this new power of 3 over 2, but it's really overcomplicating things to write down divide by 3 over 2, so it's simpler to say multiply by 2/3, and let's have a plus c at the end. So this then simplifies to give me 1/3 when I deal with the constants, and then of course, I want to replace u with 2x plus 1, and then plus c at the end. So again, think about the original question, 2x plus 1 to the power of a half. You can see that the power of 2x plus 1 has been raised by 1, and yes, we did divide by 3 over 2, but we've also got this factor of a half here to think about. Now think about how that relates to the original question. So as you can see, the examples build up to be a little bit more complex each time. So we have the integral of 5 over the square root of 4x plus 2. Now I'm going to rewrite this. I'm going to pull the 5 outside of the integral. So this 5 here is going to come outside of my integral. And then I'm going to rewrite the denominator So the root of 4x plus 2 as 4x plus 2 to the negative a half. Now identify your inner function. Here it is. U equals 4x plus 2. Differentiate. Du by dx is equal to 4. And then we're going to do our faux rearrangement. Dx is equal to du over 4. So from here, let's start doing the actual substitution. Make a little bit of space here. So that 5 can just remain where it is. We'll incorporate it in the answer in the end. And then we want u raised to the power of negative a half. And then in place of dx, I want to go here and replace it with du over 4. Now again, I'll pull that 4 out of the front of the integral. So we've got 5/4. The integral of u to the negative a half du. Raise the power by 1 and divide by the new power as we do the integral. So that's going to become u to the power of a half, but dividing by this new power, dividing by a half is the same as multiplying by 2. So I'm just going to write that. And then we can simplify this to 5 over 2 u to the half. But of course, we know that u is the same as 4x plus 2. So we have 4x plus 2 to the power of a half plus c. And again, can you spot the link here between the original integral and the final answer? The power is being raised by 1, we're dividing by this new power, but then a few other things are going into the calculation as well. Now, our last example, we've again got a factor here of 10, which I'm going to pull outside of the integral. And then this denominator here, I'm going to rewrite as 3x plus 1 to the power of negative 3. And then we have the whole integral with respect to x. Identify your inner function, u, which is 3x plus 1. Then du by dx is equal to 3. And then let's do our faux rearrangement. Dx is equal to du over 3, and then we can make use of this in a second. So this is 10 multiplied by the integral of u to the power of negative 3, and then in place of dx, we want du over 3. So again, I'm going to pull out that factor of a third into the denominator outside as a multiple of the whole integral, and it just makes the integral a little bit simpler if we can focus on u and then just deal with all the constants afterwards. So we've got 10/3 here. Now u to the negative 3 becomes u to the negative 2, divide by the new power negative 2, and don't forget to add on a constant. So this then simplifies to negative 5/3 u to the negative 2. But of course, u, we know, is the same as 3x plus 1. So we need to put that back in. Now, again, look at the original integral, look at the final answer, see if you can spot the connection that takes us from here to here in one step. And we're going to see if we can explore that in more detail in a minute. So I've picked out 4 of the examples that we've looked at, and we're going to look at the original integral and the answer in a little bit more detail. So let's start with the first one, x plus 6 to the power of 7. This became x plus 6 to the power of 8 all over 8 plus a constant. So you can see that the power of 7 has been raised by 1 to make 8, and then we've simply divided by 8. So that example, very, very simple. Now the second question was a little bit more complex. 3x minus 7 to the power of 4 was being integrated, and it became 3x minus 7 to the power of 5, but the final answer was over 15. Now, what we need to remember is that 15 is the same as 5 times 3. So yes, we have divided by this new power of 5, but we've also divided by the derivative of the innermost function, which is, of course, 3. So we've divided by the 5 and we've divided by the 3. Now, does that happen on the next example? Well, let's see. So 2x plus 1 to the power of a half. Well, let's try it. 2x plus 1. We'll raise the power by 1, so it becomes 3 over 2. And we'll divide by this new power of 3 over 2. But we're also going to divide by the derivative of the inner function, which is 2. And because we're dividing by the 3 over 2 and by the 2, we're dividing by the product of these things. Now, of course, there's a plus c as well, which we'll just take for assumed here. So this then gives us a value of 1/3 2x plus 1 to the power of 3 over 2, which is the answer that we got if you look back at this question. And so that leaves us then with one final example where there's a 10 here at the start. Now, that 10 is just a multiplicative factor which will appear at the end. We have 3x plus 1, and it's being raised to a power of -3. So we need to raise that by 1 to -2, and we need to divide by the new power of -2, but we also need to divide by the derivative of the inner function, which is 3. And so this leaves us with a final answer of -5 over 3, 3x plus 1 to the -2, and of course there's a plus c as well. And if you check back, this matches the answer we got for the last example. So we want to generalize this. So in general, if we have the integral of k brackets ax plus b to the power of n being integrated with respect to x, then the answer to this will be k, which is just a multiplicative constant, ax plus b to the power of n plus 1, all divided by n plus 1. So we're dividing by the new power, but we also divide by the derivative of the inner function, which means we divide by a. And of course, there's a plus c at the end. Now, notice in the generalization, I didn't have the integral of f of x with respect to n. I very specifically had ax plus b, because this only works if the inner function is a linear function. So it has to be a function of the form ax plus b. We can't have any other powers of x. So it's really crucial that if you're going to employ this quick method of integration by substitution, that the inner function has to be a linear function. Now, if you're not comfortable with this, it's absolutely fine to use the full process of integration by substitution, setting out u and following the process through fully. So now it's your turn. You can either do these two examples using the full integration by substitution process, setting up u equals and then following the process through, or you can use the quick generalised result that we have just seen. Notice in both cases, the inner function is linear. So either pause the video and try these yourself and then check the answers, or follow this through with the video. I am going to use the quick version of integration by substitution. So I want 4x minus 1, which is a linear function, remember, to be raised to the new power of 7. And of course we need to divide by this new power of 7. But I also need to divide by the derivative of the inner function, which is 4, and then include a constant. So my final answer, 1 over 28, 4x minus 1 to the power of 7 plus c. Next question. Again, a linear function, 1 minus 3x is being raised to the power of -1/2. Let's increase the power by 1 to 1/2. Now, dividing by 1/2 is the same as multiplying by 2, so I'll just put that in as a multiply by 2. But I do need to divide by the derivative of this inner function, which means dividing by -3. And then of course, plus c. So the final answer, negative 2/3, 1 minus 3x to the power of a half, plus a constant. Now, we're going to have a look at two further examples using integration by substitution, and in both cases, there is a more complex function, and part of this is not linear, which means we cannot use the quick method. We've got to use the full method of integration by substitution. So let's take a look at the two examples. Number one, x bracket x squared minus 2 to the power of 3. Now have a look at this and you can see, hopefully, that it's certainly the x squared minus 2 part being raised to the power of 3 is not linear. So we've got to go with the full process. But what is our substitution going to be? Well, it's going to be this part here. U is going to equal x squared minus 2. So notice this time, interestingly, du by dx is equal to 2x. And that's very important. When we do our faux rearrangement, dx is equal to du over 2x. So there is a 2x in this derivative. So let me go back to my integral. I'm just going to make myself a little bit of space here. And my integral is the integral of, now, there's an x here, which I'll leave there. And then we've got u raised to the power of 3. And then in place of dx, we're going to replace that with this, du over 2x. Now, notice something. Some of you may have been worried about that purple x, but worry not, because it will cancel out with the x, which is part of the derivative here. And then you're then left with a half, which I'll pull out of the integral of u cubed du. So we end up with a simple integral after all. So that's a half u to the power of 4 over 4 plus c, and then tidying this up we get 1/8, and then of course I want to replace u with x squared minus 2, and we are finished. Let's try another example which is similar to this. This time it's a quotient rather than a product. So again, it's not a simple linear function, and we can't just make use of the quick integration by substitution process. What we can do is set u to equal this. So u equals x squared plus 3, and du by dx is equal to 2x. Now that's a common theme in these questions, where one part differentiates to another part, which means that there will be a cancellation. So notice there's an x here, there's an x in the original integral, some sort of cancellation is going to occur in a minute. Let's do our faux rearrangement. Dx is du over 2x, and then let's start substituting in. So my integral is equal to the integral of x over the square root of u, and then in place of dx I want to use this, so du over 2x. So again, notice that convenient cancellation occurs just like last time. So I want a factor of a half out here, and then instead of 1 over root u, let's make that u to the negative a half, and then let's follow through with our integral. So we have this factor of a half here. U is now going to be raised to the power of a half, and then dividing by a half is the same as multiplying by 2. So we've got this. So we've got u to the power of a half plus c, which is x squared plus 3 to the power of a half. Now, you need to notice in both these examples, one part of the function differentiated to another part of the function. And that is a crucial theme that you will come up against again when we look at integration by substitution and further examples. Now we're going to finish off with two examples that involve definite integrals and how we can do these using integration by substitution, because of course we need to think very carefully about the limits. So my first example, x squared multiplied by x cubed plus 3, is being integrated between -1 and 3. Now notice that one part of this, x cubed plus 3, differentiates to another part of this. So this is beautifully set up for integration by substitution to work, because we know when we do the substitutions there will be a cancellation. So u is going to equal x cubed plus 3. du by dx is going to equal 3x squared. And we can already start to see that a cancellation will happen. Rearrangement, dx is equal to du over 3x squared. Now, let's start to substitute in. I'm not doing anything with the limits just yet. I'll come back to those in a second. So remember, we have this x squared here. We then have the square root of u, and we should have had a dx over here, which I'm going to put in now retrospectively, and which we will replace with du over 3x squared. Now, the cancellation that we were expecting occurs, and we're going to be left with 1/3 outside the integral of u to the half du. But the reason I've paused here is because we haven't dealt with the limits. Now, these limits here are in terms of x, but our integral is in terms of u. The limits and the integral must match, so we have got to convert the limits from being in terms of x to being in terms of u. So we can do that very, very simply using the fact that we have this substitution here. U is equal to x cubed plus 3. So look at our limits. Our lower limit was originally x equals -1. If we substitute that into this result here, this gives me u equals 2. So my lower limit here in terms of u is 2. Now, what if x equals our original upper limit of 3? This then gives me a u value of 30. So I've got 30 in there. So I can now do my integral, and it becomes u to the 3 over 2. Remember, we're dividing by this new power, 3 over 2, which is the same as multiplying by 2/3, and we've got limits of u equals 2 and u equals 30 to substitute in. Now, we do not need to put the integral back in terms of x because we changed the limits. So from here, we're going to leave in terms of u as we have converted the limits. Now, if we didn't convert the limits, then we would have to put the integral back in terms of x, but we would then have to use these limits here rather than these limits here. We now have an integral which is in terms of u, we have limits which are in terms of u, so all we have to do is substitute in these limits. So we know that this is going to be 1/3 of 2/3 multiplied by 30 to the 3 over 2, take away 2/3 multiplied by 2 to the 3 over 2, which is probably going to give us some decimal value. Now, we can actually express the answer as a surd if we want to, using our calculators, but we get a decimal answer of this. So I'm going to round that to 35.9 to 3SF. So let's look at the final question. I'm going to do this using two methods. Now, the first method is going to use the full integration by substitution process. So u is equal to 2x minus 1, du by dx is equal to 2, and then doing the faux rearrangement, dx is equal to du over 2. Now, because this is a definite integral with limits, I also need to convert my limits as well, which I'll do very clearly here. So I have x equals 1, which is my original lower limit, and if I substitute that into this result here, what does that give me? It gives me u equals 1. I also have x equals 2, which gives me u equals 3. So my integral is now ready to be converted to an integral in terms of u. Lower limit 1, upper limit 3, and then I have 1 over the square root of u. Now, instead of dx, of course, I'm going to write du over 2. And then this is really just ready for us to do some simplification. Let's make a bit of space for clarity. So this then becomes a half, the integral of u to the negative a half du between 1 and 3. Now, integrating u to the power of negative a half gives us u to the power of a half. But of course we need to divide by the new power of a half, which is the same as multiplying by 2. But what's quite convenient is that this a half will cancel with this 2 here. So we then just need to substitute back into the result here. Now remember, we don't need to convert back in terms of x because we changed the limits to u, which means the whole integral can now just be done in terms of u. So we get 3 to the power of a half, which is the root of 3, subtract 1 to the power of a half, which is just 1. So there's the full process in action. Now, if I want to use the quick method here, I can, because look at my integral, it's 2x minus 1 to the negative a half. This is a linear function being integrated, 2x minus 1. Now, if I use the quick process, all I have to do is take 2x minus 1, raise it to the new power, which is a half, divide by the new power, which is a half, which is the same as multiplying by 2, but also I need to divide by the derivative of the inner function, which means I need to divide by 2. Now, again, we get a cancellation here, and I can keep my limits as 2 and 1 because the whole integral has stayed in terms of x. So when I then substitute in, I've got 2 times 2 minus 1, which is 3 to the power of a half, take away, 2 times 1 take away 1, which is 1 to the power of a half, and I get to root 3 minus 1 using this process here. So make sure you understand the difference between what I've done in each process and why each method has led to the same answer. In the first method, I changed the variable to u, which meant I needed to change the limits to u as well. In the second process, I just carried out the integration using the quick method, which is known as inspection. And by doing the integral by inspection, I was allowed to leave it in terms of x, which means my limits are in terms of x as well. And this is one of the great things about this process. We can do questions in lots of different ways.